Okay, so good afternoon, everyone. Welcome to the last talk of the workshop. So my name is Zhongliang Zhao. I'm currently a postdoc researcher at University of Bern in the research group of Professor Thomas Brown. I guess he was here yesterday for a short panel discussion. So the title of my talk today is a tutorial of mobile multimedia wireless sensor network OMNeT simulation framework. So I have to mention the work before, because I got some review during my submission that I should give a very practical hands-on course for this tutorial, and in fact this was the work we have been finished around 1.5 years ago, and I was, before coming here, I was trying to setting up a virtual machine which includes everything. However, since I was traveling in conference and I just arrived this morning, I was not managed to set up this image. And then in this talk, I am not able to really give you this image. Then we can start really practice. But I will just try to give you some general information about our framework. And in the meantime, our framework has been uploaded to our group webpage, and it's open source. But currently we still have the password protection, but we plan to remove it, and we will also put let's say very detailed menu about how to set up everything, such that I mean everybody is interested in easily get to know how to play with it. So here's the outline. First, I'll give you a short introduction about this multimedia sensor network, and then more focus will be given to our framework called M3WSN, which is the mobile multimedia wireless sensor network frameworks. Then I will show some, I will grab some results which we have been performed to evaluate the protocol which has been implemented using our framework. Finally, talk will conclude with some remarks or implications. So as we all know, that the sensor network has a very wide range of applications, and if we have these multimedia sensors, then it has a larger potential. I mean, compared to the traditional sensor, which only sends the scalar data. So a multimedia sensor can have this real video transmission. So I mean, from end user point of view, it's very clear you can see what is transmitted over the network, not only the packet stuff. So then, of course, it has a lot of potentials, and it permits a wider range of applications which require audio and video transmissions. And this includes traffic collision avoidance, and environment monitoring, and video surveillance, and also a lot of smart home, smart city applications. So in the mobile multimedia sensor network, mobile communication are enhancing the multimedia sensor network scenarios with mobility supports, such that the objects to be monitored are mobile. Okay, and for example, like cars and people, animals, those are naturally mobile. And these mobile sensors equipped with sensor cameras and could be used to explore and sense the different areas which are of interest to the monitors. So the motivation of our work, as we know that when we start to analyze some protocols, and always start with doing some simulation work. And also the solutions involving multimedia video transmission must be evaluated from the end user's perspective. So this is one of our key contributions of this work. And also because video flows normally have very different characteristics depending on their, this IEP, different frame types, and also a group of picture size and different coding mechanisms and so on and so forth. And so multimedia transmission or evaluations require really the video-related data, such as frame types and or delay of the jitter requirements. If it's a it's a surveillance application, then delay normally has a high priority. And also have to make certain coding errors, and also we have different inter and intra-frame dependencies. So more motivations. Normally, mobility trees enable the understanding of how network protocols and algorithms behave on a different mobile case, and this will enable a more, let's say, complex mobility scenarios, and as expected in many smart city applications. So as we know that OMNeT is a standard and general purpose simulator employed to study protocols in wireless and post-wireless networks, and our framework focus more on the wireless part. And however, at the current OMNeT framework, lots of different Castalia or INET, MANET do not provide large set of mobility models, and I'll also show that our framework also uses the ball motion. And another key contribution from our framework that does not, the existing work does not support the multimedia video transmission and evaluations. So the general picture shows the three frameworks. First is Castalia, and it has very advanced wireless channels, and it's very easy to follow the architecture, and also from the coding perspective. However, it does not provide video transmissions, and also not provide an easy way to evaluate the video transmissions. And in the meantime, if you want to do this video transmission in OMNeT communities, there are two open source framework. I guess this OMNeT, I guess it's from like university in UK. They propose the use of moving objects, for example, in these intruder detection applications. So this framework provides that certain objects can move in followed by certain mobility models, and it also provides these object detection functions. So, and however, it does not provide video transmissions also, and it also does not support complex mobility models. And their another framework is from a university in France, and it's called WVSN. So it defines a concept called field of view, which means to define the sense range of a camera node. So as we know that in scalar sensors, everything's omnidirectional, it's wireless transmission. However, if you have a video, one camera can only cover a certain range of the area. So it also introduced this notion of cover sets and different application criticalities. And however, in the meantime, it also does not provide the real-time video transmissions. Okay. So based on these two frameworks, we have proposed, like we could see it's integration of the previous two frameworks, this OMNeT and WVSN. We call it mobile multimedia wireless sensor network, in short W3MSN. So it's relied on the Castalia architecture and integration of both OMNeT, which means includes moving objects and object detection. And it also includes some functions from WVSN, which means we also support with the field of view and cover sets and different application criticalities. And so in general, what WSN, the M3 WSN provides is provides the whole implementation of new functions to provide mobile multimedia management, and it supports delivering, controlling, and evaluating a real video sequence. And we also provide different scenarios, including fixed and mobile nodes, as well as moving objects. And we also implement or provide certain mechanisms to measure or to evaluate the impact on benefits of these different video-aware algorithm and protocols for both fixed and mobile scenarios. Here is the architecture of our framework. I guess lots of components are the standalone Castalia framework. Just something I should mention is that in this sensor manager part, here we have the sensor standard trees, which includes the the transmission of the real video trace. So as far as a sender wants to send some trace, it has to generate the trace and send it on top of applications. And on the receiver side, it has to receive the traces. And for the rest, I guess it's all the typical Castilian components. And so, as I said, currently we didn't observe any framework which provides direct real-time video trace transmissions. So that's why we have to port this tool called FOV, which provide video-related information. This includes which frame are lost or received and their types, and delay of or jitter of every transmitted frame, and all the decoding errors, and also the inter and intra-frame analysis of all the transmitted frames. And so all this video-related information which are supported or given by the tool FOV will enable the creation of a new assessment and optimization for static and mobile multimedia sensing applications. So in addition to this support for real-time video transmission, our framework also enables definition of energy consumption values for retrieving every frames, and this can bring you some benefits when you design some energy-efficient video transmission protocols. So, some general picture about video transmissions, video trace transmissions. So, when the sender wants to send a video trace, it has to, of course, prepare this trace, encode the trace, and so here this video trace part contain all the relevant information about every frame that consists of the video that will be transmitted. This means it includes all every type, the type of every frame and the size of the frame, and the EDP, or I mean also the moment when the frame will be sent. And this frame this trace will be generated and will be encoded in different frames and will be sent. And when the receiver receives this, the same procedure will be repeated and vice versa. So yeah, here one piece I skipped. So the source node has to create this sense trace for every video transmission, and so in general it includes at which time slots which packets are sent with certain size. So in the receiver side, the destination nodes creates a receiver trace file of every received video. So it also includes a sequence of video frames. So which frames are received at which time slots with certain packet ID or with certain payload size. So as I said, multimedia video transmission should be evaluated from end user point of view. This means a user should see clearly that this video is of good quality or of bad quality. So, and currently there are basically two types of evaluation metrics. It's called objective or subjective. So in objective, there's three metrics. For example, this peak signal to noise ratio, and also this structural similarity means to measure the similarity between two continuous frames. And there's the third metric called video quality metrics. So in this, in the later, I will also show the SSIM value and VQM value using our framework, certain protocols, of course. And then also the subjective metrics, for example, this main option scores. Okay, and we also use this bond motion such that we can generate different mobility traits, support different type of mobile scenarios. Yes, so that's new. So we use our framework to evaluate different protocols, of course. And our application scenarios is intrusion detection application using multi-tier network. Means we have two-layer network first layer is deployed with scalar sensors using omnidirectional sensing array. And then the upper layer consists of different camera nodes which only has certain fixed field of view. So the story is like whenever an intruder enters the area and it's detected by scalar sensors, and scalar sensors will send a learning message as soon as possible to the upper layer, such that to close the video camera will turn their angle to turn the field of view to the coverage of that scalar sensor which detects the intruder. Okay, and then within this layer of camera nodes, a message are transmitted using one of our produced work. We have a QoE-aware FEC mechanisms, which means to create redundant packets based on the frame importance. So as we know that FEC is a standard redundancy creation mechanism to create redundant packets such that in case certain messages are lost and you can recover it. However, we don't do this for all the frames. We do this only for frames that are of important types. And we're using this RS coding for creating the redundant packets. So in case of the packets, certain packets are lost, the original frames can be recovered from redundant packets. So we set up a bunch of simulation parameters, and then we evaluate the performance using, as I said before, objective metrics like this SSIM and VQM. Also the subtractive evaluation means that the real transmitted frames, you can clearly see that these frames, I mean the one in the center part, quality compared to the original frames. You can clearly see whether it's good quality or not bad quality. And also we compare, we see the performance of network overhead to see whether our FEC aware, QoE aware FEC can reduce overhead or not, and whether in the meantime it can keep the similar or worse or good video quality. Maybe I go to this part first. So as you can see, this is device defined. We call it intruder. So this is the original frame which was captured from the center side. And then if we apply this no FEC, which means we don't transmit any redundant packets, then we can see there are a lot of distortions from the receiver side. So it's not very good. And if we also apply this very simple typical FEC, of course the quality is improved a lot. And if we apply our QoE aware FEC, you can see the quality is slightly worse than the simple FEC, but much better than no FEC. But we have quite important improvement concerning the number of redundant messages. So we reduce network overhead quite a lot. And 2 slides back, this SSIM measures the similarity between 2 continuous frames within the video trade sequence. And it normally has a value ranging from 0 to 1, and a value closer to 1 means a good video. And as we can see that the green curve is our QoE aware FECs. It's achieved more or less similar performance as the simple FEC, which are all better than no FEC mechanisms. And the second matrix is VQM. It's also another very typical matrix for evaluating video qualities. And for this matrix, a value closer to 0 is a good video. And we can also see that our FEC aware, QoE aware FEC, which is the green one, is also closer to the simple FEC, but we have reduced the overhead. Yeah. Okay, so as a conclusion, we have proposed this M3 WSF framework, which supports real video sequence transmission. And it provides key video-related information which can be used to create new assessment and evaluation and optimization solutions for mobile wireless sensor networks. And we also, our framework provides QoE evaluations, which is only possible through the transmission of a real video sequence. and it also supports different video trees to enable the understanding of network in different scenarios. And the code was available here, and we will, as I said before, because currently we have the password protection and we only give access to some of our official partners, but we plan to remove the password protections and also upload detailed instructions of how to play with the frameworks. But I have to mention that since this work was done around 1.5 years ago, so I guess we were using OMNeT 4.1 or 2, might be some. So in case we upload everything, I guess we will upload a virtual image, a virtual machine which includes all the whole version of OMNeT. And currently it's, because this is an outcome from a project which has been finished already from 1.5 years ago. And currently we don't have plan to port everything to the new version of OMNeT. Just to let you know this. Yeah, that's all. Thank you.
Thank you. And I guess we have time for a couple of questions.
When you were doing the video scoring, were you delta scoring from the original video? In other words, if the original video captured was of only modest quality, then you could get a really good copy of that and still be only of modest quality. But you've done your job by transporting what was there. So is there a comparison to the original video to generate those quality scores?
I think here what we did is we randomly select a certain frame within the video sequence. Then as I show here, you can really see the quality of a certain frame. Then you know whether the quality at the receiver side is similar to the original one or.
Okay.
Here is, I think we randomly select a frame number. Then, I mean, of course, if once I didn't mention that the quality of the video transmission depends on the complexity of the movement, of course. If the video is of a lot of movements, and then from the receiver side, it might be a lot of distortion during the transmissions. And however, if the guy is moving very slowly, then of course the quality could be kind of good.
Okay.
So additional questions? Well, maybe I can hook in with a question between, as it's like the multimedia mobile wireless sensor node framework. What kind of other applications do you see? And in this case, you consider like tracking a person, transmitting video streams over. So what kind of other applications do you aim for? What do you think that people will use the framework for? Once it's available?
This is a simulation work, okay, and I guess when the project was still running, we planned to implement the whole thing in this camera, CMU3 camera node. We plan to deploy a real testbed. I guess this has a lot of application like this, I don't know, building surveillance or monitoring. But as I said, we didn't really continue the work to have the deployment, to have a testbed deployed.
And can you go back to the architecture slide at the beginning? Because I think there were certain components that might be interesting for other people, certain parts maybe, how modular is the whole thing at the moment? Can we take out parts and then maybe
as I said,
port them to new INET versions or integrate them?
I don't know whether you are familiar with Castalia, because Castalia is quite normal for sensor simulation, right? It's a sensor simulation. I guess it could be. I'm not sure how the interface among different layers are they similar to the INET, or because I didn't really work on INET. But for sure, if you're really interested in this video transmission part, then these two modules, sender trace and receiver trace, which is responsible for decoding the video sequence into a sequential of video frames, and encoding, and decoding the transmitted video frames into a sequence. For sure, these are, let's say, generators can be ported to different layer of different framework like INET or INET Manet. Yes.
And generally, from the the ability to, let's say, a different radio, let's say a Wi-Fi radio and better cameras. It's easily possible.
Yeah, yeah.
Okay.
No, here is nothing independent on camera. No. I mean, we were using this
You can
FOV.
feed whatever, you can feed
Yeah,
whatever
you,
you can.
you can exactly inject any video sequence
Mhm.
for this simulation. It's independent of the which video sequence you're choosing.
I'm interested in how you are assessing the video performance. I mean, are you doing that online while the simulation is running, or you
No.
you are doing so that
Yeah, offline.
Because I think
Yeah.
I suppose Evalvid does this.
Yeah. Then you have as all the frameworks, you have a bunch of output files, which includes. I didn't put it in the frame. If you check the paper, it includes which nodes received which frame type at this time, and so on and so forth.
So you can check.
Yeah.
But my question is, how can you use the quality of experience online if you are measuring it at the end of the simulation? This is the thing I'm not understanding. Maybe I'll just lost some piece.
Could you just repeat?
So you said that you are using an algorithm that is quality of experience aware.
Yeah.
Yeah, but you are measuring the quality of the experience just at the end of the simulation.
Yeah.
So
Because when we create the frame,
yeah,
our approach does not create redundant packets for all the frames. We create redundant only for certain frames, which are, for example, iframe, which has.
okay. So you are.
Well, depending on the type of the frame.
Yeah. Okay.
If the frame is if it's I, then we create 100% duplicate. If it's P, then we can only compose. We only reproduce I think half. There's another paper which refers to all of these mechanisms. You can also check.
Yeah, because I know there are some algorithms that are trying to work to use quality of experience online, and they just try to they avoid sending, for example, B packets when the network is saturated.
Yeah.
So in this case, you are sending all the packets, but you are just protecting the most
the important one. Yeah, we create 100% of redundant for important for I frame, and for P frame we create half of it, and for B we don't create it. I think this is but you can double check. What's including. In the
just think that this way probably you are.
It's kind of static. Maybe.
Yeah, you're maybe the risk is that you are increasing congestion. Just because you are adding. I'm just guessing online in this case. Okay, thank you.
So we still have time for additional questions.
Is there any opportunity to send redundant information for only part of a frame?
No. Currently, no. Currently, it's per frame. Yeah.
Yeah, because it's a monolithic
Yeah, because
frame.
we're following this IPB frame within the group.
Because you can picture how my cell phone camera can pick faces out. That would be a really interesting enhancement to just have the faces sent in redundant strong video. And the background is, who cares, there's a pipe on the wall.
That sounds good.
But it's part of the protocol.
That sounds good.
Next up.
So, any more questions from your side? Well, then, let's thank the speaker again.